All right, I know why you're here. You came to get that one question, that burning question, answered. Why in the world do we care about p-values? That's what we're going to do here today. And we're going to do that starting with the discussion of categorical independent variables. We're going to dive into Jamovi in just a second. So if you haven't already downloaded Jamovi, or if you don't have it open, go do that now. If you haven't imported the data set, do that now. I'll give you a second. All right. Categorical independent variables. That's what we're going to work with in this video. We talked about in the last video categorical versus continuous variables. If you haven't watched that video, you don't know what I'm talking about. Once again, pause this video, go watch that one. We're particularly interested in categorical independent variables today. Independent variable, for those of you who don't remember this from prior statistics courses, independent variable is our predictor variable. It's the thing we're going to use to predict some outcome. The outcome is the dependent variable. So we have this outcome variable, and we're going to see if there's a relationship between the independent variable, the predictor variable of interest. We have some sort of hypothesis that there's a relationship. And so we're going to work with categorical independent variables, and I'm going to show you a couple of basic analyses. But first, I think we have to ask the question, who cares whether p equals 0.05? Or maybe actually the question we need to ask is, what in the world do we mean when we talk about p is less than or equal to 0.05? Well, it starts with the idea of a null hypothesis. Null hypothesis is like one of the weirdest things in statistics. Imagine we have a hypothesis, some sort of theory, some sort of idea that there's a relationship between one thing or another. Our null hypothesis is the thing we're trying to reject. The thing we're trying to reject. It's counterintuitive, makes no sense. I'll give you an example here, and then we'll actually try that example. Imagine our hypothesis one, the hypothesis we're actually wanting to test, our theory. Our hypothesis one, individuals born in an even birth month perform more poorly than those born in an odd birth month. That's our hypothesis. That's the thing we're going to test in just a moment. Our null hypothesis starts with the assumption, and we notate this, by the way, using H0. Our null hypothesis then is that there is no difference in performance for those born in an even month and those born in an odd month. And this is actually important. We always need to be thinking about what is the null hypothesis that we're trying to find evidence to disprove. Importantly, we're never really going to be able to prove our hypothesis. All we can do is to provide some support for our hypothesis by providing some evidence that we can reject the null hypothesis. So in all of our statistical analyses, we're trying to find statistical evidence that we can in fact reject the null. And the null is often unstated, but I think it's really important for you to be able to articulate it. What is the counterfactual? What is the inverse of your hypothesis? So make a practice of stating your hypothesis and then stating the null hypothesis, and make it a practice of speaking in terms of the hypothesis that we're going to reject, that null. Now, this is important in this particular case and in every case because we need to have some degree of confidence in what the statistics tell us in order to feel good about rejecting the null hypothesis. As I put this hypothesis up here, individuals born in an even birth month perform more poorly than those born in an odd birth month. I put that up here in large part because that sort of strains believability. It's hard to imagine why that might be the case. There's no logic behind it. People's birth months are random. There's no logical reason why we would expect people who were born in an even birth month to do more poorly. And so the burden of proof, the burden of inspiring confidence in rejecting what our current understanding or belief of the world is. Our current understanding or belief of the world is the null hypothesis. In order to convince you to reject your current understanding, the null, I have to give you statistics that inspire confidence. So how do we get that confidence? Well, that's where the p-value comes in. That's the thing. When we can reject that null hypothesis, statistical significance is the point at which we can reject that null hypothesis with less than some established likelihood that the difference we observed is based on chance. There is always a chance that the difference we find, imagine we find a difference. Imagine we find that people born in odd birth months actually have higher performance scores than people born in even birth months. Now our job as statisticians, as inferential statisticians, is trying to determine to what degree or what is the likelihood that we would observe that difference based on random chance. And there are a few things that contribute to our interpretation of that chance. So first of all, how far apart are the average performance scores for people born in even versus odd? If they're only 0.0001 apart, well, all things considered, there's a reasonable chance that that's due to chance, right? Also, the distribution of the underlying data, whether there's a wide variance in performance in each population or whether the variance is very, very low contributes to that. You don't need to know all that. What you need to know is traditionally when people talk about statistical significance, what they're saying traditionally, what they're saying is that we want to have a 95% confidence level that this is not due to chance. We're willing to accept 5% chance that this difference is due to chance. But we want 95% confidence. Therefore, we want a p-value that's less than 0.05. We want a p-value that says that we're only going to see this result based on chance less than 5% of the time. That p equals less than or equal to 0.05 is basically saying that this difference that we've observed in our data is only going to happen by chance 5% or less of the time. So that's what we're looking for. Anytime we do some inferential statistical analyses, the level of significance we're going to impose on it, the amount of chance we're willing to accept on average is going to be 0.05, 5% chance that this is due to chance. Make sense? I hope it does. If not, rewind, watch it again, maybe and fast forward this time. But now we're going to go actually do a couple of analyses with this understanding that we're interested in this p-value of less than or equal to 0.05. All right, I'm in Jamovi. I have that same data set opened up. Remember, we're working with categorical independent variables. Turns out we have a lot of categorical data in our data set here. But we're going to pick a couple of basic analyses, and we're going to start with t-test. The two analyses we're going to use in this video are t-tests and ANOVA. They're similar conceptually. There's some differences. The differences aren't particularly important right now. You can explore those differences. The key difference is that t-test is for two populations. If you've got an independent variable with only two different groups, and ANOVA is if there are more than two populations. That's the main thing. That's the main difference. And you can play around with that. You can test out different data sets. You can certainly use an ANOVA for a categorical independent variable for which there are only two conditions. For example, our data, we have gender here as 0 or 1. One is male, one is female. We can use an ANOVA for that, but we don't have to. We can use a t-test. So let's start with a t-test. I've already imported my sample data set here, so you can follow along while we're doing this if you want. But we're going to do independent samples t-test. And you see, again, the results window opens up, and it's all ready for me to tell it what analyses or what variables I'm interested in. Our primary hypothesis is that group 1 is not equal to group 2. We might have slightly refined hypotheses. We might have a specific theory that one is higher or lower than the other. For the moment, don't worry about that. That sort of changes the basic assumptions of the analysis, but let's just stick with the basic hypothesis that there's a difference or not that one is necessarily always higher than the other. And let's just for fun, let's look at our dependent variable. The variable we're interested in predicting is manager rated performance review 2. That's our dependent variable here. And let's do the analyses that I was referring to just a moment ago. Let's do the analysis. Let's even birth month. This is a binary categorical variable that takes the value of 0 if a person was born in an odd month, and it takes a value of 1 if a person was born in an even month. So that's going to be our grouping variable here. Now you'll note that it's telling us that it'll accept dependent variables that are continuous. It will also take dependent variables that are categorical, although the math is a bit more crude. It's not the most interesting and exciting thing. And the last thing I do before we close this video out is show you how to create a continuous variable here, because you'll know we don't have many. manager rated performance 2, and even birth month is our grouping variable. That's the variable on which we're hypothesizing a difference. And Jamovi just very quickly does the analyses here, and interestingly enough, look at this. So we're seeing that manager rated performance review 2, the question, the manager's rated performance on question 2, the t statistic is negative 1.97. The t statistic is not particularly important, other than to note that it turns out 1.97 is a pretty important t statistic because that's associated with that 0.05. If you get a t statistic of 1.96 or higher, you've suddenly reached that point at which the p-value is 0.05 or lower. So it turns out that what we actually find is that those who are born in an even month perform significantly lower than those born in an odd month at a 0.05 level of significance. So we actually find support for our hypothesis here. Now that's weird. I got to tell you, you shouldn't have expected that. We actually find statistical evidence that we can reject our null hypothesis. Our null hypothesis was there's no difference between those born in an even and odd month. Now you should be very bothered and worried about that because it turns out that this is actually just pure chance. I randomly assigned birth months to these folks. Randomly assigned them to one of two groups here. I have no idea what month they were born. So I actually inadvertently created some randomized data that pops out as showing that there's a statistically significant difference, which tells us something really important, that we can't actually prove anything using statistics. All we can do is throw up some statistical evidence that helps us gain confidence in rejecting the null. But even at our statistically accepted levels of confidence, I'm showing you here that there are times where we find relationships that actually do not exist. Actually, what I found here is a relationship between randomly generated data and performance. That's a note of caution. We'll talk about that later, and we'll talk about how to deal with that, because that's important to note, that sometimes you find things using statistics that are not real, that don't actually represent anything in real life, but we mistakenly imagine they do. We'll come back to that later. The main point here is that you now know how to conduct a t-test, and hopefully you know how to interpret the t-test. We now know that there's a difference here, and we can combine that with the mean difference statistics. A mean difference is 0.158. That's mean difference is 0.31. The average performance level for those born in an even month is 0.31 lower than the average performance level of those born in an odd month. Average performance level for those born in an even month is 0.31 lower than those born in an odd month. That's a t-test. An ANOVA is very simple. Interacting with an ANOVA is exactly the same thing, except for you can put a grouping variable here that has more than one category. I'm going to let you do that. I'm going to let you play around with those. I've showed you the main thing I want to show you on categorical independent variables. We can use that categorical independent variables to predict a lot of things. We can the t-test or ANOVA to predict a lot of things based using categorical independent variables. We can look at the relationship between gender and, for example, the stress that employees might experience, the relationship between gender and employees' job satisfaction or intent to quit. We can look at the relationship between whether or not a person's a newcomer and how well they perform, or their job satisfaction or intent to quit. And you might instinctively have some hypotheses around these, but I'm going to encourage you to, as you write your hypothesis, also articulate the null hypothesis and interpret your results as in the frame of, does this provide us evidence such that we can reject the null hypothesis or not? Final thing I want to show you is how to create a calculated variable. So I told you in the first video that these variables came from a couple of surveys of employees, and then surveys of their managers. So this manager rated performance 1, 2, and 3. I want to create those were 3 individual survey items related to performance that the manager completed. The idea here is that there are 3 ways in this organization of thinking about performance, but performance is sort of the average of all 3 of them. And you can look at the data here. We can look at this particular person. question number 1, the manager rated them as a 5. On the other 2, they rated them as a 3. Conceptually or theoretically within this organization, these 3 individual ratings wrap up into a single rating of performance. So what I want to do is I'm going to create a calculated variable that effectively is the average of all 3 of these. It turns out it's pretty easy to do. We're going to insert a variable at the end. And we're going to do a computed variable. Sorry, I'm going to delete this variable. And we're going to do a computed variable. We're going to call it ag performance. And we're going to use create it with a formula. We're going to do the mean. We just hit that function mean. And now we have these parentheses, and similar to Excel, it allows you to just drop in whatever. You can create some math in here. And what we're going to do is we're going to do the mean of manager rated performance review 1, comma, manager rated performance review 2, comma, and manager rated performance review 3, comma, and we hit enter, and suddenly we now have a calculated performance score down below here called ag_performance. And it's the average of those 3 variables. And you can go through and double check the math if you don't trust the software. But what we've effectively done now is we've created a variable that Jamovi interprets as a continuous variable, and it does that because it's got a wide variety of decimal places here, and we have a much wider range of numbers. So Jamovi is now interpreting that as a continuous variable. And that's useful because now our analyses can get a lot more intriguing. So first of all, our t-test. Let's look at a same t-test we conducted earlier using aggregate performance as our dependent variable and even birth month as our grouping variable. Oh, interestingly enough, we still find a significant difference. Once again, we found some evidence that statistically significant evidence that we can reject the null hypothesis of no difference between odd and even birth month people. But when we go back to exploration, when we go back to our descriptives, we can now see some interesting stuff. We can look at aggregate performance, and we can split our aggregate performance based on even birth month, that categorical variable, and we can do some interesting stuff like we can look at a box plot, or it's sometimes called a box and whisker plot. What the box and whisker plot is doing is it's giving us the mean, the average, as this line, this horizontal line for each of the 2 populations. It's giving us a box that represents some number of standard deviations away from the mean, or some proportion of the data, and then it's showing us the entire range of data with the whisker here. And you can intuitively sort of imagine that a situation where the box in one situation was much lower and the box in the other situation was much higher. This is sort of approximating very crudely the distribution of the data within each of these populations. We can look at a histogram here. Again, the histogram is split by whether a person is even birth month or not. And we can look at what the underlying data look like. We can look at a density plot. We can remove the split. Look at all those same data to look at the individual distribution. The main point here is with a continuous dependent variable, now suddenly our ways of thinking or describing the data get far more expansive, especially when we're thinking about describing the data graphically. Final thing we can do is we can look at a scatter plot. Scatter plot, we can look at aggregate performance on the y-axis, and we can look at intent to quit on the x-axis. It's sort of crude. It's not particularly useful because there are not a lot of different. There's not a lot of difference on the aggregate performance score. But what this is telling us is if we scatter, if we looked at the relationship between intent to quit and someone's performance, this is what the relationship looks like, and we can do a regression line which shows us what the relationship might be. And it's sort of suggestive that the more likely a person says they are to quit, the lower their performance is on average. But it's crude. It's not particularly useful. There are much better ways to do this. I'm merely showing this to you because now you've sort of been Now you know you're sort of exposed to all the various tools you can use to describe data, particularly once we have some continuous data. All right, I'll see you next time.